One of the most important ideas in this course is the idea of eigenvectors. Eigenvectors and eigenvalues show up in all parts of mathematics, differential equations with modeling stuff, applied things related to network sciences, and God knows what else. All kinds of things that you would least expect to be eigenvectors are eigenvectors. For example, if you've ever heard of El Nino, the weather trend, that's an eigenvector. If you've ever heard of Google, the PageRank algorithm is an eigenvector. So we'll talk a little bit more about that hopefully later on. A scalar, a number lambda, is called an eigenvalue of a linear transformation. So let's call the linear transformation L. And so it's taking vectors from V and it spits out vectors from V. So lambda is an eigenvalue of L if there are non-trivial solutions to this equation right here. So this is the eigenvalue equation or the eigenvector equation. And you can see that there are definitely always trivial solutions, right? Well, the trivial solution always works. L of 0 is always going to be a scalar multiple of 0, namely 0, right? So we're only interested in the case when this thing has non-zero solutions. And such non-zero solutions are called lambda eigenvectors of L. So lambda is the eigenvalue, V is the eigenvector. The eigenspace of lambda is the subspace, which is the collection of all eigenvectors like this. Well, eigenvectors plus 0. So 0 itself is never, ever an eigenvector. Okay, so the significance of this idea is that we're looking for a generalization of the notion of fixed point. So a fixed point in mathematics is a point such that when you apply the function, you get the same thing back again. Right now, we don't, with linear functions, you don't often have fixed points. So the next best thing you have is a fixed subspace, a subspace that gets mapped to itself. In the case of a one-dimensional subspace, this means that the vectors don't change direction. They just change their length. So they get scaled. That's the meaning of this equation right here. The vector v, what happens to it? It stretches. It might get stretched by a negative amount and point the other way out of the origin, but it stays on the same line that it started on. And then with two-dimensional eigenspaces, it's something similar, right? You've got a plane such that anything from that plane gets mapped back into that plane by the linear transformation. Okay, so I said this thing was called the eigenspace. Why the word space? Well, because it's a vector space, right? So let's check that this guy is a vector space. All right, so it's been a while, but for old time's sake, let's go through this. So if you want to check that something's a vector space, let's see. Does it contain 0? Well, yes. Okay, we already went through there. 0 always satisfies that equation. So let's let x and y be elements of E lambda, and let's choose some scalar c for when we check scalar multiplication. Okay, so the meaning of this, the fact that we chose x and y to be from there, we know that L of x is lambda x, and we know that L of y is lambda y. All right, so let's see. We need to check additivity. So is x plus y an element of E lambda? Well, how do we figure that out? Well, you're in E lambda exactly when you satisfy this equation. So in other words, if I apply L to the sum, I should get lambda times the sum. So let's check. So we apply L to the sum, and we use linearity. And then we use the fact that, well, here, let me just write this. So this is by linearity. And then we use the fact that we chose L of x so that it would be equal to lambda x, and we chose L of y so that it would be equal to lambda y. And then we factor out. So this is true because x and y are eigenvectors. And then the last one is just, well, distributing. Okay. So we went from L of the thing to lambda times the thing. That's exactly the relationship we need to be in E sub lambda. So x plus y is an element of E lambda. All right, what about scalar multiples? So is the scalar multiple cx in there? Well, we need to take L of it. And we can pull out the L, or sorry, we can pull the C out of the L because L is linear. And then we chose x, so that L of x is equal to lambda x. And then we can rewrite the scalars whatever order we want. So there's lambda times cx. Okay, so then that shows that cx is also in E lambda. All right, so together those two facts show that this is indeed a vector space. So observe that E lambda consists of all the lambda eigenvectors together with, we have to throw in 0. And we have to throw it in because the 0 vector is never, ever an eigenvector. Now, this is 0, the vector that I'm talking about here. The number 0 can be an eigenvalue. That's fine, because you can send a vector to 0 as part of a linear transformation, like multiplying by the 0 matrix will do that, or a projection will do that. That's totally fine. Because one of those vectors is going to get scaled down to becoming 0 because it ends up being 0. So that's totally legitimate. But the 0 vector is never an eigenvector, and I make a big stinky point about that because at some point you'll be doing a calculation and to try and find an eigenvector, and when you read the results of your calculation, it'll tell you, oh, your answer is the 0 vector, at which point alarm bells should ring and you should go, oh no, wait, I made a mistake. I screwed up the arithmetic somewhere. I got to go back and fix it, because 0 is never an eigenvector.